Right. Okay, so let's go ahead and get started. Next Tuesday, as promised, is going to be our first midterm for this class. The scope of the midterm is actually a little bit less compared to last semester. We are moving a little bit slower than before, like last semester and the semester before last. So I will only go up to addressing modes for this semester. However, we are a little bit slower than usual, also because this is the first semester that I introduced Johnny. So that means, Johnny will also be a part of the scope of this test. Okay? So we'll take a look at some kind of familiar, questions first, just so that you know what kind of question I might ask you, or what kind of question I have asked in the past. So these are all exam questions that have already been asked in the past. So let me click on this guy here, and this one has been exposed. It has been shown for some time already, so this is not really the first time it has been shown. And let's go ahead and take a look at it. I was using a different screen a little bit earlier, and somehow the size just does not match up with this screen. All right, there we go. And I have to remember to make sure the recorder is on. The recorder is on, it's recording, so that's good. Now I need to take a look at the file that I downloaded. All right. Okay, so are you guys ready for the practice exam? Yes? Okay. So let's go ahead and take a look at some of these questions. Some of these questions are out of the scope of this class. If you guys are interested, I can still talk about it. If you're not interested, we can save it until next time. Not interested? Okay. All right, if you're not interested, we'll only focus on the ones that we will, encounter in this test. Okay. And many of these are really just regular text files, so you can open it with just a regular text file. A text editor like Mousepad. Yep. Am I in the wrong folder? Yep, I am. There we go. Q4C.pdf. All right. So this is really just a text file. It's one of the more. It's one of your favorite questions. Favorite type of questions. It's a find it type of question. So in this case, you are figure out the value of EAX after a sequence of instructions to help you get to the answer and potentially get partial credit in case the final answer is incorrect. Explain the result or the effect of each instruction. All right, so we have a whole bunch of stuff here. You can see that this is pretty much the reverse of the find it homework assignment. In a way, it is easier. In a way, it is harder. But it depends on how you look at it. Okay, I think it is easier because you don't have to reverse the steps and apply algebra to find the answer. In this case, you just have to make sure that you understand the layout of memory content well enough to make so that you can kind of expect what will be the result in a particular register. And I think I might have made a mistake here, the value of EAX to be the value of EBX in this case. There are several variants of this question, and one of the variants use EAX, but in this particular one, there should be EBX, because you can see that we have been using EBX here, 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 and here. Instead of using evens, which is a PDF viewer, what I'll do instead, I'm going to use Mousepad, because Mousepad is just a regular text editor, and this way I can just add annotations to the file itself, and like changing the question to fix itself. Okay, there we go. So we have the question now. This also allows me to show you the line numbers and also show you the byte-wise allocation and memory content as we talk about this particular question. All right. So are there any questions about the question itself, what it is asking you? It's asking you about the value in EBX when we are done up to line 16. In other words, on line 19, you have to tell me the value of EBX on line 19 with the underscores. Yep.
For the lines 12 through 16, are we just putting what's going to be in the registers that they're affecting?
Right. You have to, if you want to tell me, something about the process, you can, kind of let me know, what you think that instruction is going to do, or what will be in EBX at that time.
But are we going to be graded on it?
Only if the final answer is incorrect.
Okay, so
for this particular question, okay, so your exam is going to be a little bit different. I'm just explaining, a particular past exam and how I graded it. All right. Okay, so let's go ahead and get started with this one. Let's start with the first instruction. In other words, we'll start with this one here. Okay. What do you think is going to be in EBX after line 12? Yep.
The numerical value of the address of L1, the actual address number?
It will be the address itself in EBX. Okay, very good. Okay. So what we'll do is we'll use pseudo C code, or I think pseudo C code may work well here. So EBX will end up with a value of L1. Okay, not the content at L1, but L1 the value of the label itself. Okay, if you look up the actual value of the label, it will be the same thing in EBX after the instruction on line 12. Okay. Are there any questions about the instruction on line 12? It has an immediate operand as the first operand, and it has a register operand as the second operand. No questions? Okay. If there are no questions, we'll move on to the second instruction. The second instruction to a math major is trivial, because they would just say that there's no change. You just move in whatever is in EBX to EBX, because the extra parentheses doesn't do a single thing. Well, maybe in a math class, but this is not a math class, is it? So in this class, the parentheses are important, because it tells you that we are no longer using a register operand on the left-hand side as the first operand. What is the first operand in this case?
Indirect.
It's called an indirect operand. So what is going to be copied into EBX? Well, first of all, can we use the EBX this way? Can we use EBX in both the first operand and the second operand?
Yes.
Yep. Certainly, there's no conflict here. So what are we copying into EBX? What is the first operand specifying?
The value is the address in EBX.
Yep. So it will be copying whatever is at the address indicated by EBX. So it will copy those 4 bytes into EBX itself. Okay. So if I were to explain this, I would explain it in 2 steps. Okay. So I would explain it, saying, first of all, we are going to do something like this. I'm going to get rid of all the extra underscores here. Okay, so the first thing I'm going to do is to explain the indirect operand here. In other words, I'm going to take the content of EBX, which at this point is the value of label L1. I will treat it as a pointer to a 32-bit content. If you want to be extra clear, what we can do is we can say in 32. So now we know that we are dealing with a pointer pointing to a 4-byte thing. So whatever we reference out of that pointer is also going to be a 4-byte thing, and I'll copy those 4 bytes into EBX. Is that okay? Is this notation okay with you guys? Because I'm kind of mixing up a little bit of assembly language here, and also a little bit of C language for the operation. Yep.
So would those surprises explanations on the test itself?
As long as it is clear. Go ahead.
I was going to say, is it then at this point L1 minus 4 at this point, or is it?
Yep. Mm-hmm.
Right?
So as a result of this, okay, if you want to add some more to it, so as a result of this, it's going to get the content at L1, and the content at L1 is L1 minus 4. So at this point, EBX would have the content will have the value of L1 minus 4. Is that okay?
That has nothing to do with the top part, right, does
It has nothing to do with
it? The dot in.
the dot int.
The
It has
ones that are
everything.
unlabeled. The
On
ones that
line
aren't
9?
labeled, yeah. On line 8, the ones that aren't labeled.
On line 8, no, but on line 9, yes. This has everything to do with how I initialize the dot int on line 9 and put a label L1 next to it. Yep, go ahead.
Looks like your comment, first line and third line little contradictory. Because now you passing value, and your first line you passing address and have one.
It is just the value of the label.
Yeah, but in first line it's the same notation, you passing address.
The dollar sign it's immediate operand.
No, I'm talking about comments.
The comment, that is correct.
Yeah.
Because L1 is an integer. Remember, in assembly language programming, there's no type. So EAX or EBX has no type, L1 has no type. When I just refer to L1, I'm just referring to the value represented by the label L1. L1 is not a variable. It is really just an integer value.
I mean, first line EBX equal L1 and EBX equal L1 minus 4 is like have different meaning, but you write it.
No, it's just-
L1 is the address of L1. L1 minus 4 is the address of L1 minus 4 bytes.
But in that case, wouldn't it be helpful to put it as an address, not as L1?
Maybe
Because
just-
L1
But there's no type. Remember, in assembly language programming, there is no such thing as a type.
Right.
Each label is resolved to a particular integer. Okay?
And in one instance, you could use it as a memory address, in another instance, as just the value back the address.
The way you can tell whether it is used as an address or not is to see how it is used in the instruction by the addressing node.
Okay.
In the first instruction on line 12, I'm just saying whatever L1 is, whatever that label is representing as an integer, copy that value to EBX. So I'm not using it as an address in any way. Okay, so in that context, L1 is nothing more than a regular integer that is determined by the linker and also by the loader, when I load the program. In other words, that value is not known ahead of time, but I know it is just an integer. On the other hand, when we look at line 13, if you look at the pseudo C code, even in the pseudo C code, this has no type. This is really just saying, oh, let's take a look at the register to get 32 bits. Okay, but what am I going to do with the 32 bits? The first thing we do to that 32 bit is to say, let's cast it. Let's cast that 32-bit thing, whatever it is, into a pointer to a 4-byte thing, into an in32 pointer. And then what we do with that in32 pointer is to dereference it. Is to say, okay, now we want to dereference that in32 pointer and actually grab the content at that address and then copy that to EBX. So until we do something with a particular label or a register, a label and a register are typeless in assembly language programming. Okay? The meaning, or what we know as quote unquote the type, only has to do with the time when we access it. Otherwise, it has no type. Is that okay? That is really one of the things that we have to undo from your C++ class, is to associate types with variables, quote unquote variables. Because in this class we have labels and we have registers, and neither of those have particular types. They are nothing more than just numbers. Labels have basically a constant numbers, and registers can store specific values at at whatever during runtime you can change those values. Are we still doing okay with this? Yep, go ahead.
This is an example. Well, I'm not sure what would happen if you tried to store an address in a .word. Would it just throw away the parts that didn't fit?
No, the assembler would actually complain and say that,
okay.
well, the assembler may complain depending on whether that label is defined in the same source file. If it is defined in the same source file, then the assembler can complain about it and say, nope, cannot store a 32-bit thing into a 16-bit space.
Okay.
On the other hand, if the label is defined in another file, then the assembler has no chance to complain, and it will be up to the linker to complain at that time.
Okay, and if we attempt to, will it also complain if we attempt to store a .word in EDX, which is too big for it? Or will it just store it in the other?
Okay, now we are getting back to the type thing, okay? So it depends on the instruction. If you use a move W with
right,
a,
yeah.
Thank you. Okay, is there any question I can answer? Go ahead.
So for 930, is it moving the contents? Is it moving the address?
It is using EDX or the value in EDX at that time as an address. Go to that address, grab 4 bytes from that address,
Yeah.
and then copy those 4 bytes to EDX.
Yeah.
So that's why there's a dereference operation here when I express it in C operations. Are you guys doing okay or not?
Is it going to go to that last int, define on part A, grab that, and put it in index?
Is it going to?
If it's at L1, is the lag between the last int on line 8 and the first word on line 10. It's going to go L1 minus 4, which is the beginning of that last int on line 8.
Well, that is not relevant to us at this point because we just loaded L1 minus 4, which is the content at the address of L1 at this point. That's why we're moving L1 minus 4 into EDX. But what we are going to do with that has to do with the other instructions. Any other questions? Yep.
Okay, in line 13, what do the parentheses do?
The parentheses indicate this is an indirect operand.
What is the indirect?
Well, maybe I can, help you by locating the nodes related to that. Because this is something that we kind of talked about. We have addressing modes and memory allocation. That would be the link that we should look at. Okay, so we talked about these addressing modes. The other ones, I think the way I addressed this one was I addressed the 5.10 first, which is the base scale indexed addressing mode, and then I went back and talked about the other ones as specialized versions. So they're missing certain portions of the addressing modes. In the most general form, we have the displacement on the outside, open parentheses, the base register, the index register, and the scale. Do you guys still remember this one?
Yeah.
Okay. This is the most general version of a memory-based operand, which is 5.10. This is the based scaled indexed addressing mode. Everything else can be derived from this one. So in this particular form, the effective address or the address that is being specified by this particular operand is going to be D, which is the displacement. D has to be a number that is resolved by runtime. Okay, it has to be a constant by the time we get to runtime. B is a register, so whatever the value of the register is what we use in this equation. Say again? Is there a question? Okay. I is an index register, so we're also relying on the value of the register. When we run the program up to this point. The scale is one of the numbers 1, 2, 4, or 8. Okay. Are we still doing okay with this code here? Okay. So we have the other addressing modes being basically specific versions of this one. Okay. When you look at the direct addressing mode, the direct addressing mode means we only have the D component without the rest. When we look at 5.5, which is the indirect addressing mode. So when we look at indirect addressing mode, we only have the B component. When we look at the base addressing mode, the base addressing mode specifies a D and a B, but without the index or the scale. And then we have the base indexed addressing mode, which is 5.9. That one is, okay, you can probably guess the rest. Based, indexed, but without scale is D, B, I, which has an implied scale of 1. So you can look at this one, which is the same thing as D, B, I, 1. In other words, the scale is implied to be 1. Is that okay? I mean, so that's why, I only explained this one, because this is the most general form of a memory-based addressing mode. All of the other ones are kind of like this one, but potentially with certain parts missing. But each and every single one is only calculating an effective address. The actual thing that is being copied from or copied to is memory. It is not the address itself, it is whatever is at the address. Yep.
What would be some examples of D again?
B, D. D can be a number as simple as 5, can be -2, can be L1 if
So
you
that
want.
modifies the BIS after BIS has been calculated?
It doesn't matter because it's an addition, so this component and this component and this component can be evaluated separately. And because this is an addition, it doesn't matter which way you do it.
Okay.
So it's just the effective address is nothing more than a sum of these 3 components.
Could D be a register?
No, D can only be a number that is resolved by assemble time, by link time, or otherwise by load time. It cannot change during runtime. Yep.
So if you just have D, it would be looking in that memory location?
If you just have D, then the rest are basically assumed 0. If I don't specify a B, it means it is a 0. If I don't specify I or S, that means that component is 0.
So it would just look in the D memory location, whatever D is.
D specifies the memory location, where you're copying from or where you're copying to. Yep.
So if you use a label as D, then it copies what's at that label. Not
That becomes a
itself.
direct operand, right?
And if you use a label for I, it uses the address of the label.
No, a label cannot be used by I.
Oh.
B and I have to be registers.
Oh, okay.
So these two, must be registers. That's the only thing that can go into those 2 spots. And scale can only be 1, 2, 4, or 8. You have to specify a constant for those 4. All right.
But if you only have a B, then it would be that register. It would be that.
If I only have B, that becomes, that means I'm only relying on, so that means all the other components are assumed 0, and I'm only using that to specify the effective address.
And it would take the memory location or what's at the location.
It would take the content at that memory location. In other words, if I just have B, it becomes an indirect operand, and in that case, B, or the register known as the base register, is used to specify a location in memory, but what you're copying from or copying to would be the location starting at that location.
Yeah. It wouldn't be what's actually in the location, it would be the location itself.
No, it will be whatever is at that location. There's an indirect it's an indirect operand, which means a dereference is implied. Yep.
I think I would have to use some kind of collision or something along those lines where you're choosing addresses and like grab data. If you're working with a really large program, right? You're understand how to simply uncode.
Okay, how about this? We go through, I can give you an example of, okay, how about this? We'll go through this one first, and then we'll see whether it is any further instruction is helpful in this case. Okay, so let's go through this first. So in this one, we'll go ahead and take a look at this one, and we'll say EBX in this case is, okay, should I have a dereference on the right-hand side of the assignment operation in this case? In other words, is the first operand, which is the source operand, specifying memory content location, memory content, or am I specifying an immediate operand, or am I specifying a register? That's the first operand. The second operand is clear. Okay, what does an immediate operand look like?
$sign.
It starts with a $sign. Does that start with a $sign? No. What does a register operand look like? Start with a percent. Okay. Does that start with a percent? No. No, it does not start with a percent. It starts with a number. -3 is a number. Okay, so that means it is not an immediate operand. It is not a register operand. What is left? A memory operand. Okay, one of the many variants of DEIS. Okay, but in this case, which variant am I talking about? It is already on the whiteboard. Based. Exactly, because the index register is missing, the scale is missing as well. Okay, so how am I calculating the address at which I'm grabbing the content to copy it into EBX?
You're adding the
Okay. Now, in its most raw form, it is this number. Okay. I'm taking the content of EBX when I run this instruction, and I subtract 3 from it. Okay. That number, expressed by EBX minus 3, becomes an address. So I'm casting EBX minus 3 as a 32-bit number address, and then I do a dereference, which means I'm going to that location, copy 4 bytes starting at that location into EBX. Are we still doing okay with this? So, but we do know what is in EBX, don't we? What is in EBX at this point? L1 minus 4. Very good. Okay, so if we know what is in EBX, then I have a easier job here, because now I can substitute L1 minus 4 and put that in place of EBX. So now it becomes L1 minus 4 minus 3, like that. Okay? And it becomes EBX equals to, in 32, the reference from that, L1 minus 7, because minus 4 minus 3 is the same as subtracting 7. Are we still doing okay with this code here? Somewhat. It's okay? Yep.
So, I see L1 minus 7 goes out of range of what actually gets stored. Does it?
No, it's not.
It's not?
No,
I
it's
thought
not.
it only goes up to L1 minus 6.
Why?
They're all 32.
They're not in this.
Yeah.
Okay, I can see some of the key concepts that I need to re-emphasize in this class, but that's what it's going to do. Okay, I'm not going to tell you guys exactly what it's going to copy yet, because I want to finish up the rest first. Okay, so this one is register BX instead of EBX. This is the least significant 16-bit of EBX. The first operand is L1 plus 5. I kind of gave away the answer already. But what kind of an operand is L1 plus 5? You get 3 choices. 1, it is an immediate operand. 2, it is a register operand. Or 3, it is some kind of memory operand. I don't care which one, but it accesses memory. It's a memory operand because it does not start with a $sign. All immediate operand starts with a $sign. So this one is, well, I kind of gave away the answer because of the dereference operator. I typed a little too fast. Okay, but this time I'm casting it to a 16-bit integer because I'm only copying 16-bit or 2 bytes. Where am I copying from? Exactly at the location L1 plus 5. In other words, when you have a direct operand, whatever you specify is the address that you're copying from. L1 plus 5 is the location where we are copying from. Is that okay? And then the last instruction, I'm going to just use BH here, which is bit 8 to bit 15 of register BEBX. So we're going to do it here. BH equals to, in this case, because it's a move byte, I'm only dealing with 8-bit at a time, so int 8 would do. And this is just L1 plus 7. L1 is a particular label. You can look at L1 as a bookmark in memory. Okay? It is indicating, hey, this place is also known as L1. But you can look at that as an address. You can just look at it as a number as well as an integer. Okay? In assembly language programming, there's no difference between that. Yep.
If you wanted to use base scale indexed addressing mode,
Yep.
and copy the address that you got as a result without dereferencing it,
We are not going to talk about that instruction.
Okay.
We will not talk about the L instruction.
Okay, so-
there is an instruction to do it. I'm not going to talk about it.
okay, so
Okay.
but it's not moved.
It's not move. Yeah, it starts with an L, but it's not move. Okay. All right. So now that I have decoded every single instruction, let's see what is actually going to be copied. In order to understand what is actually going to be copied, I will have to decode every single .int, .word in order to find out, what is at what location to figure out, what we are actually copying into EBX. Okay, we will start with line 8. So when we look at line 8, now this part is really, really important because by the questions that you guys are asking, or some of you are asking, I can kind of understand, what kind of concept is maybe missing, when you're looking at the code. .int is what we call a directive. It is telling the assembler, I am now going to allocate some 32-bit chunks. Okay? Each thing, comma separated, is going to use up 32 bits or 4 bytes. Is that okay? .word is switching to 16-bit. .byte is switching to 8-bit. And we're still doing okay with that concept. Okay. So in this case, I'm going to allocate 32 bits to represent hexadecimal 2B. How do I represent 2B in 4 bytes? Okay, so we'll go ahead and use the regular expression first. Now, unless I specify it is in base 10, it's going to be in hexadecimal because there's really no need to say 0x0x0x when everything is in hexadecimal already. Okay, so until I use base 10, everything is in hexadecimal. How do I represent 2B00 as a 32-bit number? How many leading zeros should I need? 4. Because 2B00 has 4 digits already. Each hexadecimal digit is 4 bits. Okay. What about 0 to B0? Okay, 5 leading zeros altogether before the 2. Okay, 1, 2, 3, 4, 5, 2B0. Okay, now the most important part here is I am still representing the numbers as 32-bit chunks, and that's why I'm still writing the most significant byte on the left-hand side and the least significant byte on the right-hand side. So the next thing we need to do is to understand what is little endian, which means we need to represent the least significant byte at the lowest address. Okay? So we'll go ahead and switch that now into the little endian representation, which is a byte-wide operation. So in this case, we have 2B being the least significant byte, 0, 0, 0, 0, 0, 0, 2B, 0, 0, 0, 0, B0, 0, 2, 0, 0, 0, 0. Okay? Are we still doing okay so far with this decoding of memory content here? Okay? the next line is kind of tricky because the next line says L1 is dot int L1 minus 4. In this case, I'm just going to say, okay, at location L1, we have 4 question marks because we don't know what is L1 minus 4 until load time, until the program is actually loaded into memory. So I cannot tell you ahead of time what it is. I just know how it relates to the label L1, and I know how L1 relates to all the other memory content that I'm allocating using .int and .word. And that's all that I need, is how L1 is related to the rest. Are we still doing okay with this? So it doesn't hurt to do the rest, even though I don't think it's going to matter. So in this case, we have .word 2b. So once again, I express the .word as 16-bit chunks first. 002b, 2b00, 02b0. And now I switch to the little endian representation using only as a byte sequence. So we have 2b00, 00, 2b, b0, 02. Okay? So if you string everything together, then we have the actual memory layout of this entire thing. Okay? So we'll go ahead and take a look at the entire thing. And I will cheat here. I know you guys cannot do this, but I can. Which is something like this. Really cool. Copy and paste. Okay. Now, can someone tell me where I'm supposed to put L1? L1 is a label of 1 single byte because the I386 is byte addressable. That means a label is only the address of 1 single byte. Which byte should I put? The first 2 question marks. That is correct. So L1 is a bookmark. In other words, whenever I refer to L1, I am actually referring to the address of that particular mystery byte. Only the content is mystery. Its location is not mystery. In other words, I don't really know where L1 is, but from here, I know how all the other bytes relate to the bookmark L1, which is all that I need. Are we still doing okay with this? Okay.
Actually.
Yep, go ahead.
So why exactly are the question marks showing up there, and why is L1 at the first question mark? Yeah.
It's because of this.
Is it because it comes after that instruction? Is that the only reason?
Well, this is the same thing as separating it into 2 lines. In other words, I can separate it into 2 lines, and it means exactly the same thing. L1 colon is basically saying, okay, look at the next location that will be allocated in this section, which is data section, and call this L1. So right after I put a label onto that memory location, I immediately allocate it and say, okay, from this location on, I want to allocate 4 bytes and initialize the content of those 4 bytes to L1 minus 4.
And why does L1 minus 4 matter? That's what I'm wondering.
Because it is going to matter when we perform these operations.
Okay.
Because I'm referring to this L1 minus 4 here. That's when it becomes useful.
Okay.
Yep.
It's there are question marks because it's a memory location which we don't know yet, but we don't actually need to know the memory location.
We do not need to know the
We just
actual
need to know
content.
where it starts.
That is correct.
So the question marks are just holders.
That is correct. The question marks are just placeholders so that when we count L1 plus 1 plus 2 plus 3 plus 4, we know where those locations are. So are we still doing okay so far? Okay. So I think we are ready to figure out line, currently on line 25, okay? Because we want to figure out what is going to be copied into EVX at this point. So let me just go ahead and highlight line 25, and we'll try to figure out what is going to happen when we execute line 25. Okay. So in other words, I'm going to tell you the effect of this particular line. guys, are we ready? Okay. All right, so what we need to do is to say, okay, what is at L1 minus 7? This is L1. This is L1 minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. This is L1 minus 7. So I'll just call this L1 minus 7. Make sure I line up the rest correctly here. All right, so we know the starting point of the copy operation. But you have to also keep in mind that we are using little endian when we copy from memory into register. Then we have to figure out which byte becomes the least significant byte. Little endian specifies the least significant byte is also basically the one at the lowest address. In this case, the 2B is at the lowest address. So that becomes the least significant byte. So the entire word that is copied into EBX is going to be 0x in hexadecimal, B0, 2B. Is that okay? What about the next instruction? The next instruction is going to copy from L1 plus 5. So I lied, it's actually important to identify the byte locations afterwards. Okay, so we got L1 plus 0, plus 1, plus 2, plus 3, plus 4. This is plus 5. So I'm going to identify this location as plus 5. I'm not going to say L1, just so that we don't use up too much space here. So the first 0, 0, or the one that is right above plus 5, is L1 plus 5. Question?
Yes.
Go ahead.
I don't understand why it's B0000002. I mean, why are we starting from L1 minus 4 and then?
Because after the calculation, it becomes L1 minus 7. Because the EBX at this point has L1 minus 4 already. We have an additional minus 3
I
outside.
understand that, but the value of L1 minus 7 is 2B.
But that's the least significant byte.
Okay.
The most significant byte is the B0 because it is at an offset of plus 3 from that
So
location.
B bits, and that's or 8, 32, right? 32.
The least significant byte is the one coming from the lowest address.
4 to the right. 3 to the right. Is what I mean.
Yeah, so the next one becomes the second least significant byte. The next one becomes the second most significant byte, and then the last one becomes the most significant byte. Yes. Well, that's why I put a label under that 2B as L1 minus 7. Okay.
With the layout of words. So
here's
you
my-
don't change it right now, but you can use that.
Well, it is intentionally confusing because I just want it to be confusing like this, and still have you guys to solve the problem.
I can understand that. That's not for example, but that's how you put it.
Well, this is not an example. This is an actual exam question from past semester.
Sure, but I'm wrapping my mind around it.
Okay, so what you can do, because you can just take the same program, change the byte sequences to whatever you want, right? Specify those byte sequences to be as unique as you feel comfortable with. Run the same program and then see whether you get the results that you expected. That is one big thing about this class is you have to spend some time with GDBs, the assembler, the linker, and the whole works in order to really get the concept. There's nothing I can explain here that can really replace the actual experimentation with the instructions. Yep.
So, EBX is the register of B00002B. That's the register, right?
That is the content in EBX at that time, as a third EBX number. EBX is a register.
And So when you write it in the Little Indian, where do you consider that stored? What's the name of that location? Not a register, but when you write it out Little Indian.
Little endian only applies when you are talking about memory location.
So that's how it's written in memory location.
In memory location, it is 2B0000B0 after
And then
location
when you
L1
copy
minus
4
4.
bytes from memory location to the register, at that point it writes it in standard.
It uses the little endian convention where the location of the lowest location, the byte at the lowest location, becomes the least significant byte. So the endianness of a processor only comes into play when you are interacting between memory locations, which are byte addressable, with multi-byte registers. Because a register is not memory content. You cannot say the least significant, the lowest address of a register. It does not apply. So when you look at a register, let's say EAX, it's a 32-bit register. You look at all 32 bits at the same time. But when you look at memory content, it is only 1 byte at a time. Each location is only 1 byte. So when you copy 32-bit from memory into a 32-bit register, we know that we're going to copy these 4 bytes into a register. But what needs to be specified is which byte becomes the least significant byte and which byte becomes the most significant byte. Because there are 2 ways to go about doing this. And the Intel processor chooses to use the little endian convention, which means the least significant byte is the one coming from the lowest location. Any other questions? No other questions? Okay. The actual location, I mean, these content here, you can change it to whatever you want. These content here, you can change it to whatever you want. It does not affect how the addressing is actually done. It might help clarify what is being copied. So when you actually run the program and you look at what is actually going to be end up in EBX, it will give you a better idea of where it came from. Okay, but this whole homework assignment or exam question is designed so that we can do everything on quote unquote the dry dock. Okay, you don't need GDB to actually do it. You can just analyze how memory is laid out without using GDB at all. All right, well, we are almost done, not quite done yet. Okay, so L1 plus 5 is over here, and L1 plus 6 is over here. So what we are doing here is, BX itself, we get 0x0000, which also means, we are overwriting the least significant byte of EBX. So if you look at EBX, it becomes B0000000, because we are overwriting the least significant byte, the least significant byte word with 0000. And then we have one more instruction to deal with. The last instruction is L1 plus 7. This is L1 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. This is location plus L1 plus 7. So the last instruction is going to do basically the same thing as BH gets 0x2B, and that only affects bit 8 to bit 15 of EBX. So when you look at the entire EBX, it becomes 0xB0, 00, and then this is the byte that is changed because it's the second least significant byte, and then the rest should still be 00. So are we doing okay so far in terms of the concept? Yep.
I have a question. If you
Yep.
wanted to store, say, 2C in BH, what kind of so like you wanted to L1 plus 7 plus as an address plus the number 1.
Plus the number 1.
So if you wanted to like
There's no way to do it unless you have an add instruction.
okay.
So that's why you need an add instruction, because the add instruction is used to actually perform addition at runtime.
Okay, so you can't
You cannot combine the content in memory and an addition and roll it into one operand. There's no way to do that. Right. Are there any questions about this answer? Except, are you sure, Tech? My calculation kind of says, something other than your answer. No? Well, I don't trust myself, and you should not either. Especially on tedious stuff like this, I tend to kind of mess it up. I cannot add one or subtract one sometimes. So I would definitely run the program and go through the program step by step to make sure that these things are actually observed and correct. Okay, so let's go ahead and do that. But you can see that you should be able to do all this without using GDB, without using any tools. Okay, that's the whole idea, is to understand memory layout and the addressing modes well enough so that you do not need to use the debugger or the assembler to do anything, and be able to just run it on a piece of paper. So let's see. Yep, go ahead.
And can you use move to a label to change memory?
Can I move?
So you can use move to move from a register to memory, though.
Yes,
right?
you can.
Okay.
Yep.
So you could use no.
That would actually make a good question. I have never had a question with moving something back into memory and then asking that question. Okay, that would. All right. So AS-G stab -O Q4
So to summarize, there's no way to you can only overwrite memory using move. You can't make changes to it without overwriting it. So you can't add one to a memory location.
Only with the add instruction.
Yeah, so you can't use move. With move, you can only overwrite.
Yeah, move can only overwrite and copy byte for byte, but it cannot add something to it. All right, so let's go ahead and link it. Q4C, Q4C, Q4C.O, and GDB Q4C. All right, so I have the program. Hey, it doesn't have the. Oh, you know what? I forgot to do one thing. I forgot to save it. Do you guys want me to save it so that this shows the comments too, or is that okay?
We're fine.
We're okay? I did not change the instructions, so it will still run exactly the same way. You know what? I'm gonna do it. Oh, got to go back here. Make sure we save it first. You can probably tell how this can actually cost me in terms of turning in homework assignments, right? Link GDB list. Much better. So this time we got everything here. All right. Okay. So we are now stopping right before the first instruction. We'll single step this instruction and then take a look at EBX, just so that we know what L1 is. And then from that point on, we can use the examine instruction or the examine command in GDB, so we can actually cross-check every single thing that I talked about. Okay. All right. So single step. Take a look at EBX. And EBX has this, value, which seems kind of random. It is 8048060 in hexadecimal. So the first thing we want to do is to double check and say, okay, can we double check memory content starting at the very first place that we allocated and see that those are the actual byte locations as I predicted in the file. That's the first thing we want to do. Okay. Now, if you go back to the file, into the source file, how many bytes am I supposed to examine and from what location? This is L1 here, so how many bytes am I supposed to go back to the first 2B, all the way down here?
4.
Well, there are two ways to go about doing this. L1 is here. We have 3 dot ints before, and each dot int is a 32-bit thing. So we have 12. Okay, L1 minus 12 is the very first instruction or the first location. What about the last location? In other words, what is the location corresponding to this byte over here? That's the last byte location. That will be L1 plus 4, 6, 8. So that would be L1 plus.
21.
Sorry?
Page 21.
From the very beginning?
Yeah.
21.
Might be off by 1.
So the entire length of the memory allocation is how much?
22.
22, yeah, 22 sounds like correct, because we have 12 here, we have 4 here to make up 16, and then we have 6 more here, so that makes 16 plus 6 is 22. So we have a total of 22. All right. So this is how you run the X command. I've shown this several times in class. So we say 22. Each byte is printed in hexadecimal, and then you need a cast here. So we have a char pointer cast of L1. The address of L1 is casted to a char pointer first, and then we subtract 20. Nope, not 22. We subtract 12 to get to the first location, because the first location we want to examine is L1 minus 12. The casting is required because in GDB, every label has an implicit type of an int, which is useless as far as we are concerned, but it does. So are we doing okay so far, with this examine command in GDB? Okay. All right, so we'll run it. All right, so let's double check and make sure that this is the one. This is the way I kind of predicted. So we have 2b 0 0 0 0 0 0 0 0 4 zeros. So 2b followed by 4 zeros, and then we have another 2b with 2 0 zeros. 2b 2 0 zeros. We have a b0 b0 0 2 2 additional 0 zeros, and then we have 4 mystery bytes. So these are the 4 mystery bytes here. And then coming back to here, after the 4 mystery bytes, we have 2b. And then we have 2b, and then we have 0 0 0 0, 2b, b0, and then a 0 2 at the very end. So the entire byte sequence is displayed in GDB the way it is supposed to. Any questions about this? Go ahead.
In GDB it says L1 plus 4 instead of L1 minus 4.
It's L1 plus 4 because when it finds a location has a particular label close to it, it will try to print it out. And that location turns out to be L1 plus 4. So when you look at the B2B after the 4 mystery bytes, that location is L1 plus 4. And that's why it sticks that little quote-unquote label over there, just so that, hey, you know what? This location is also known as L1 plus 4. I don't know why it doesn't do it to the other side, like L1 minus something. That would be handy, but it does not. All right. So that comes in pretty handy. Now the other thing we also want to do is, what do you think? Now this is a question to you. I will run the command, but I do want to ask you first. Okay, what do you think this will show you? But what is it going to print? What is it going to print as a hexadecimal number? Go ahead. 2 bytes, because a W in GDB is 32-bit. Okay. So what do you think would be the value it is going to print?
It's going to show up 8050C.
No.
It's only
Go
going to
ahead.
have 0048050C.
I think it's 08.
Not 5C, you're close. No, you're right. 5C is the correct answer.
805.
Shit, I can't read.
8048005C is the correct answer. Okay. Now how do we know that?
This right there, part of this thing with this chart over here.
This byte is 2B, right? So that's L1 plus 4, L1 plus 3, L1 plus 2, L1 plus 1, L1. Okay? Wait, but if this is L1, how come it's not printed out as 5C800408? It's because of little endian. Okay? This is the least significant byte, this is the most significant byte. When we print it out as a 32-bit number, we print it out as 8048050C. Yep. All right, well, let's double check and make sure that is the case. Yep. All right. So are we still doing okay so far? Okay. I'm going to second step. I'm going to single step the second instruction. So here comes the second instruction. And according to my notes here, after the second instruction, EBX should have L1 minus 4. In other words, the very same number that I printed a little bit earlier should now be in register EBX. Okay, so we'll take a look at EBX, and sure enough, it has 804805C at this point. I'm going to single step the third instruction. This is our third instruction. After this, EBX should end up with B and then a whole bunch of zeros and then 2B at the very end. Single step IR EBX. And we have B followed by 5 zeros and then the 2B, which is the way it's supposed to. And then we execute the fourth instruction now. We should end up with B and then followed by 7 zeros in this case. So single step IR EBX, B followed by 7 zeros. And this is our very last instruction. Single step, and we should end up with B, 3 zeros, 2B, and then 2 more zeros. IR EBX. That's exactly the way it turned out. Are there any specific questions about the addressing modes or how memory is laid out? Are there any questions about the other addressing modes, other memory addressing modes being a specialized case or specialized cases of the most general form with BBIS components? Go ahead.
Yeah, will you ever be working with the numbers for memory locations, or is it always? I'm sorry, with the registers?
Scales.
With the numbers for the registers, will you ever be working with the numbers for the registers in memory? Will I ever have to worry about that?
Registers don't have a memory address.
Can you ask the question again? I'm not understanding the question itself. Just see if you can ask me in a slightly different way.
Yeah, I don't think so. I'll probably ask later. It's fine.
Okay, when you can think of a way to ask it in a different way, let me know. Yep.
Can I ask you about the GDB command you used?
Okay.
Why did you do the char star?
Because otherwise it becomes, because L1, as far as GDB is concerned, L1 is an integer. It does not understand that L1 is just a label. And so we have to.
It prints out the same thing if you just do L1 minus 12.
Are you using the X command?
Yep. Same command that just instead of doing all the chars, I just did L1 minus 12. That works. So,
Okay.
So why are you doing that?
I think that might have to do with the version of GDB. You might be using a different version than I am.
Oh. Sorry.
That's okay. No problem. Go ahead. Yep.
So we've been working on labels. If we were to not use the labels, could we still execute a similar command? Like how would you be able to do that? Just out of curiosity.
Okay, without label L1?
Yeah, like there's no L1.
Okay.
I still want to.
That's a good question. The question is, what if this program does not have a label L1? Now we still have one label, even without L1.
Okay.
We have underscore start.
Underscore start. Got it.
Yep.
Okay.
So we can still make use of underscore start, but that means I have to do everything relative to underscore start, which means when I load L1 into EBX, that very first instruction has to be expressed in terms of underscore start minus a particular offset. And then when I initialize the dot in on line 12, I also have to express that as I also have to re-express it as underscore start minus a particular offset to achieve the same result.
So could you change then line 27 to instead of being L1 plus 5, could you do underscore start plus 17?
No, it's going to be underscore. It's going to be underscore start minus something, because underscore start is defined after the last dot.
Oh, okay, so it would be
definition.
underscore start minus 1, 2, 3, 4, or whatever. And that would
You know what? That makes a very good exercise. Okay, I would suggest it as a brain teaser and also an exercise. And if you guys want me to disclose the answer, I can do that on Thursday, because this is on next Tuesday. The exam is on next Tuesday. So we still have one more class meeting for you guys to ask questions. But I would suggest that you guys go through the exercise. Change this program so it has exactly the same effect as it is now. But the only thing you can do to it is to change references to L1. Get rid of L1, the label definition L1 itself. Change all references to L1 to something else. We have one label that you can make use of, because everything is actually in the doc text section, including underscore star. So I would say that would make a useful exercise out of this whole thing. Yep.
I remember what I was trying to ask.
Go ahead.
Because, you know, we're stepping around in memory around L1 and L2 and whatever, right?
Right.
Are we ever going to have to do the same thing with registers? To like step in memory with
There's
registers?
no way you can step into a register, because registers are not a part of memory. So when you look at the register, you look at the entire thing as EBX. Okay, there are only 4 registers as far as the first exam is concerned that we need to know about. Is EAX, EBX, ECX, and EDX. They do not have addresses because they are registers. So registers do not have addresses. Each one is a 32-bit register, but they can also be accessed as 16-bit registers when you do not use the E part. So AX, BX, CX, DX refer to the least significant 16-bit of each of the 32-bit registers. And then we have the low part, AL, BL, CL, DL, and the high part, AH, BH, CH, and DH. The H refers to bit 8 to bit 15 of the register.
Right.
The low part refers to bit 0 to bit 7 of the registers.
But they have nothing to do with memory at all?
No,
Okay.
nothing at all. Right. So is that particular question okay? I mean, and of course it's getting recorded as well, just in case. And let me double check. Yep, it's still getting recorded. Do you guys want to go through another one like this? Yep.
Yes.
Yes.
What kind of questions can you ask about Johnny?
Okay, the question that I can ask about Johnny is going to be, I will give you the microcode of a new instruction. You know, so I would probably call the new instruction like mystery or something like that, and I will ask you, okay, what does it do? So I will give you an exact scenario. Okay, these are the content at these particular memory locations. This is a new instruction. Tell me what this instruction is going to do. How is it going to affect the accumulator and also the other memory locations, if any? If it does make any changes, what is it going to do?
It's gonna be in the exam?
Yep.
So like Johnny exam?
Yep. Except you won't be running Johnny. You'll be using a piece of paper and your mind to run the simulator.
There's not gonna be a picture.
But it is open book, open notes. Don't forget, it is open book and open notes. So that means what you need to do is to look into the Johnny documentation and look up every single microcode and find out what it does.
Jump and all that stuff?
Hmm?
No jump, add and all that stuff?
Well, there are several ways to look at it. Okay, question? Go ahead.
Yeah, you mentioned in your in the archive that's up there, your cheat sheet. Is there an updated copy of that for this exam?
No, not yet. I have not worked on the cheat sheet for this particular test, but it is something that you guys can work on. All right, so this is Johnny. All right. All right, so are we ready? Okay, so this is Johnny. What you guys need to do is to figure out, okay, what I will be asking is I will give you a new instruction. And with the new instruction, I will give you the exact instructions in microcode of what it is supposed to do. In other words, I will give you a sequence of something like this, using exactly the same notation, okay? And then you have to tell me what a particular instruction is going to do. So I will give you the microcode for that instruction. I will give you the instruction, the opcode of the instruction. So the high part of the instruction will specify the entry point of the microcode entry here, and then the low part will specify something that the instruction may require in order to finish its operation. Okay? So what you need to do is to figure out, okay, what exactly is ACC colon equals 0? Well, it zeroes out, it resets the content of the accumulator. Okay? What about INS to AB? INS to AB is taking the least significant 3 digits from the instruction register to the address bus. So it presents it onto the address bus, which also implicitly means, we are going to address memory next. Okay? The next one is RAM to DB. It takes the content of the RAM, okay, random access memory. Whatever location that the address bus is specifying, it will be out of here. So RAM to DB is going to say RAM content in RAM into the data bus. So it will be presented onto the data bus. So now we have plus. Plus is specified here, which means we are going to add whatever is presented on the data bus with whatever is in the register and store the result in the register. PC++ is over here. PC++ means we are increasing the program counter, so it will be incremented by 1. MC colon equals 0 means we are zeroing the microcode counter, so we will go all the way back to location 0. So it's ready to fetch the next instruction.
Okay, so
Yep. Well, he raises his hand. Go ahead.
can we have like a picture of this map?
Absolutely. If you can take a screenshot out of this whole thing, print it out on a piece of paper, it's all good. So you can take anything you want. Okay, you can watch my video and say, hey, this frame is what I really need. Okay. Take a snapshot out of that one frame, print it out, and bring it with you. How do you take a snapshot? You press the pause button, you point your camera to it, you take a picture, you take your film to long struts, PDF, develop the film, you get the print back, and now you have your cheat sheet on print. Well, that's why I give you 1 week to do it, because it will take you about a week to get a film developed. Yep. Sorry? No. Only one question will be based on, and it has to do with microcoding. You can print anything. I mean, it only comes with its own documentation, in case you haven't noticed. And there's a documentation folder, and there's an English version of the documentation. Let me show you what I'm talking about. All right, so let's go here. Use another window. Okay, I know we are not, we don't speak German, but I would say, Doku, gives you the best chance of being documentation out of the 3. And in here we have both ODT files and also PDF files. So I would go with the ODT file since I have LibreOffice. So LibreOffice Johnny manual.en. And here we have the full documentation. And I'm just going to find the documentation on the microcode part so that you guys can quickly locate it. Nope, does not have that. Let's try something else. That was a question. Somebody raised their hand. Yep, go ahead.
It wasn't me really, but what's the format of the test again?
The format of the test?
Like, how many questions? What type of questions?
I have not settled on that yet. Okay, here's the other documentation. Let me see. Yeah, neither one, explains the microcoding. So you probably will have to kind of experiment with the microcode a little bit and find out what each one is going to do. But most of the instructions that you have seen already, they already demonstrate what each block is going to do. So that gives you an idea of what those microcode is going to do. And by the way, each one is a button too. So if you want to execute just one microcode, you can click on that button and see what it does. And the entire source code is also available. I would not suggest printing out the entire thing, but I think looking into it may be helpful. I'm not kidding. Someone turned in, as for the first homework assignment, I think several people, not just one, several people turned in almost an exact implementation of Johnny in C++. Well, I wouldn't say exactly the same. It's like minus the graphical user interface and all that stuff, but it was, an emulator. And I was impressed. I was going like, wow, that. I was thinking that's really going all out. I mean, I didn't really ask for anything that complicated, but someone did.
Extra credit?
I think it deserves extra credit for sure. Okay, but this is the actual instruction here, and let me see if I can find the microcoding part. I can explain on Thursday. If there are any specific questions about the microcode part, I can explain that on Thursday. But I need to know which microcode you want me to clarify. Certain things are pretty easy. ACC : 0, okay? It resets the accumulator to 0, right? So you need to let me know which one you want me to clarify, and then I can write in the instruction just to exercise. Yep. It will be everything that I talked about in the lecture, except for what I say about Microsoft. All right. Yep, go ahead.
All right, so for the address bus to the radio, does it actually replace the location you're accessing?
Okay, hold on a second. Let me bring it up first. Okay, which one are we talking about?
Address bus to
Okay, hold on a second here. We are not done yet. We still have 2 minutes or so. Just hold on 1 second. Okay, go ahead.
when you're putting it into the address bus.
Okay, which block are we talking about?
When you're putting them, like, I don't want to entering into
Okay. Okay, the question was, about these two buttons. This one takes these 3 digits here, the 3 digits in blue, and present it onto the address bus. Whatever you present on the address bus controls which location do we want to read from or write to next. Okay? And then the other one is PC to address bus, which means the content of the program counter is presented onto the address bus. So we are grabbing whatever the program counter is pointing to in the content of memory. Is that helping? Yeah. Okay. So that's the kind of question that I want you guys to ask on Thursday. Very specific. I need to know, what this one button is going to do. The best way to do this is really to record your own sequence. You can create your own microcode using this mechanism here. You can basically just say, record macro, and then from that point on, whatever you click here becomes the instruction sequence, the microcode sequence that is recorded for the instruction that you are creating, up to, I think, 10 steps. Yep. I think I have to remind myself to go to the Dollar Tree to buy like a whole big stack of basic calculators, because I don't want you guys to use a phone, but I still want you to have the benefit of a basic calculator, just in case. So, I'm going to bring, like a stack of simple calculators that you guys can borrow during the test.
How simple.
You can add, you can subtract, you can multiply.
I have a TI Inspire, so.
How come you don't want to use it like?
Can I use that one?
I don't think you need base conversion. Okay, anything that requires base conversion, I will do the base conversion for you.
This can save text options.
Well, that's exactly why I would provide basic calculators. I think that's fine, TI 34 is fine.
Are we going to need a calculator?
I do not think so, but if you feel better with a calculator, I will have, like a stack available. Yeah. Okay, the question is, do we need to go from base 2 to base 16?
Why are you giving an idea?
Well, you won't finish that though, you won't, right?
I'm not going to give you any particular base conversion problems. So, for questions like what we just went through today, we're all in base 16 already.
But okay, just give us something, like, okay, just give us like 1 0 1 0 1 1 0 0, and please tell us, convert that into like decimal.
Okay, now, given that I'm not going to require any base conversion, you will have to pay attention to the way I write the numbers. 0x is a prefix of base 16. Without any prefix is base 10. With a 0 as a prefix is base 8. So all of those conventions that we use in C, you have to remember all of those conventions. It's only going to be between base 10 and base 16. I don't think there will be any other bases. Base 2? Well, base 16 to base 2 is an easy conversion, right? There's no need to have it. Right? Well, I'm going to the lab, so in case you have any questions, anyone with specific questions about Johnny or about the addressing nodes, you can go to the lab and I can try to answer those questions.